Okay, this is take 4, but that's okay. Today we're going to talk about section 3.1. This is on power functions and polynomial functions. So let's hop right into it. Let's say that I have this square, like I do on the left-hand side, with a side length of L. If I want to write a function for the area of the square, I might say that A of L is equal to L times L, because if one of my side lengths in this square is L, then the other side lengths are also L. Squares have the same side length for all of their sides. And this is equal to L squared. Similarly, if I have a cube like I do on the right hand side, and I wanted to find the volume of this cube, then I would write a function v of L that was length times width times height, which ends up are all the same thing in this case, right? Because cubes, in a cube, all of these side lengths are the same. So length times width times height becomes length times, or L times L times L, I suppose, which is L cubed. So for the area of this square, I have A of L equals L squared. For the volume of this cube, I have V of L equals L cubed. These are both examples of power functions. Power functions are functions that are some power of the variable. Notice that in this A of L here, that I'm raising L to the second power. In this V of L, I'm raising L to the third power. This is why they are power functions. So let's look at a formal definition of a power function. A power function is a function that can be represented in the form f of x equals x to the p, where the base is a variable and the exponent, p, is a number. So my exponential base is this variable, which is x in this case, and this exponent p is a number. So let's look at maybe some examples. Let's determine which of these toolkit functions are power functions. Out of these toolkit functions, which of the following are power functions? Let's see, the constant function. This is f of x equals c. Is this a power function? Well, f of x equals c can really be written as, say, f of x equals, let's say, c times x to the 0th. Because remember, anything to the 0th power is going to be 1. This ends up being just c, right? So the constant function is a power function. F of x equals x to the first, the identity function, or I spoiled it by accident. F of x equals x can also be written as x to the first power. Because I'm raising x to some power here, this is also a power function. Let's see, the absolute value function, I'm not raising x to any power in the absolute value function, so this is not going to be a power function. For the quadratic function, you see I have f of x equals x squared. because my variable is being raised to some power, this is a power function. The same thing goes for the cubic. I have f of x equals x cubed. My variable is being raised to some power, which makes this a power function. For the reciprocal function, we have to be careful. F of x equals 1 over x is the same thing as x to the negative 1 power, which makes the reciprocal function a power function, because I can rewrite it in a way that has x being raised to some power. Similarly, the reciprocal squared function, f of x equals 1 over x squared, this can be rewritten as x to the power of negative 2, which makes the reciprocal squared function a power function. For these last two, the square root function, f of x equals the square root of x, can be rewritten as x to the power of 1/2. So because I can express this as x being raised to some power, the square root function is a power function. It simply has a fractional power, but that's okay. And the cube root function is going to function similarly, because the cube root of x can also be rewritten as x to the power of 1/3, which makes the cube root of x also a power function. So actually, out of all of our toolkit functions, we only have one that isn't a power function, and that's absolute value of x. All right, I'm going to stop the recording here, and I'm going to break this up into some smaller sections.